Hello, welcome again. My name's Phil Winder and I'm the CEO of Winder.AI. This is the third and final video of a series that I've been doing about deep reinforcement learning. It's a practical deep RL tutorial. It was first performed at ODSC in London a few weeks ago, and this is the final part. So first, a little bit of admin. As usual, feel free to ask questions in LinkedIn comments or YouTube comments or whatever software you're watching this through. Just use the comment section. And slightly unusually this time, I'm going to attempt to have a look at those questions as we're going through. And the reason for that is because this section and this part of the course is all about a practical workshop. So I've got a few practical examples that I want to go through. We'll get to that in just a minute. But first, let's just recap what we've done so far. In part one, we looked at some RL reinforcement learning intuition. I explained what it is, how it's useful, where it can be used, and I presented a selection of examples in some example industries. In the second part, I then delved into a framework to help you develop and spot RL problems in the wild. It was a very long presentation. Actually, I think it was well over, it was over an hour in the end, just on that one individual part. That was last week. We talked a lot about the key challenges involved in developing an RL project and what you need and what you don't need, what's important, what's not important. And then the final section that we've got this week is some hands-on examples. I've got 2 examples to show today. And I want you to be able to ask some questions as we're going through it. And also feel free to ask questions about RL in general, you might as well ask the questions there. So regarding the examples, there's 2 examples. I'm going to try and go through both of them. I think we've got time. It would have been great if we had more, but as you can imagine, we're quite busy at work at the moment. There's a lot of movement in the AI space at the moment, so rather busy. So unfortunately, I haven't had too much time to invest in new examples, but there's one new one from ODSC, and there's one previous one from our book. Okay, so let me just add some slides so you can see what I'm talking about. So this is just a recap of what we've done before. I've just talked through that. And here is the book again. So, of course, all of the content that I've been talking about over the few days, it's a mixture of practical experience from clients we've been working with in the RL space, plus a large amount from my book. There's a lot more detail in there if you're interested in going into depth. And one of the examples we're going to look at today comes from this book as well. If you don't have time or opportunity to ask questions on the comments, then feel free to send me an email. I'll put these back up at the end so you've got the links to that. All right, so let's try and get everyone acquainted with the examples. I'm just going to dive straight in here. Where is the link? I think I've hidden it incorrectly. Let me just unhide it. In fact, I can just show you. I think you can see this. I might just need to reshare my screen a little bit, but basically all of the examples that we're going to look at today are in a Git repository here. It's github.com/philwinder/ODSC. That's Open Data Science Conference, ODSC-2023. Okay, and then when we go there, I'll just leave that link up for just a little bit longer. I think it's maybe a bit more obvious there, possibly, on that slide. And then I'm going to start sharing my other screen. I should have just shared the whole thing. Let's just share the whole window. There we go. There we go. And you can see GitHub repository, and in there there's 2 links. Actually, there's 2 notebooks effectively. There's one called Intro to RL, and there's one called Kind Trump GPT. I think let's have a think about which order we're going to talk about this. I think I might do the second one first, if that's okay, because it's a bit more fun than the first one. The first one's a bit in depth and a bit detailed, and I feel like if I do that straight away, I might lose some of you. So let's do the fun one first. So if you click on that opening the collab link there, you'll probably get a warning for the first time. First off, if you don't want to download the notebook and run it locally, which is of course fine. If you want to run it on Colab, then you need a Google account. So I'm just logged in. And the first time you run it, it'll also probably say something. Are you sure that you trust this person? And you trust me, right? There's no Bitcoin miners in here, I promise. So this first example is quite a good example at discussing some of the possibilities of RL. It's not like a full-on industrial example. I would have loved to have provided a bit more of a heavy industry type example, but this is kind of on topic. And what I'm doing in this example is I'm taking a large language model and using reinforcement learning to fine tune. Actually, you be a bit careful a little bit here. Actually, we're not fine tuning the model in this particular example. We are training a model to decide what the next best inputs are to force a language model to produce certain data. So think of it as overlaying a large language model rather than fine tuning, because obviously you can use reinforcement learning to fine tune as well. But that's not quite what we're doing here. So in this example, I kind of set out trying to do something a bit fun and a bit funny. It's always great when you've got an example that's funny. And there was a really great repo called TextRL, which inspired me to write this example. Basically, TextRL has a big selection of code that is used to pre-train various LLMs on data sets. And Eric Lam is the author, and he's gone to the effort of generating a few of these large language models for this repo. And one of them was an LLM trained upon Donald Trump tweets. There was another one for Elon Musk and a few others as well. I chose the Donald Trump one. And then what I thought, what it would be great is a lot of his tweets are not very nice. So can we attempt to alter that LLM to produce nice tweets? So the whole goal is to take that LLM, use reinforcement learning to feedback and retrain the overall sort of wrapped algorithm to produce a nicer output. And the definition of nice is defined by the reward function of the RL agent, and the reward function is defined as a sentiment classifier. It uses a sentiment classifier to detect the sentiment. If it's negative, then it negatively, or it punishes the underlying agent's behavior. If it's positive, then it rewards it. Okay, so let's start going through this now, sort of line by line. The main repo is TextRL, but that's also based upon another library called PFRL, which is another repo by the same person that implements some RL functionality, some RL algorithms. Okay, and then just a load of imports. And here we're starting to get to the meat. So with any large language model, you need the tokenizer that was used to generate the embeddings, or ultimately generate the embeddings for that language model. So we're loading the pre-trained tokenizer from the final trained output of from the Donald Trump data set, and he's uploaded it to this location, and this is a helper function to basically download the tokenizer and download the model. There are other models available here. We're then loading that model into memory. Quick tip: if you are connected on Colab, you can change the runtime. Come on, connect. There you go. You can change the runtime to where is it? Manage sessions. Oh no, it's not manage sessions. Oh, it's already there. Okay, so you can actually you can see that we're already connected to a GPU there. Let me just go back again. Manage sessions. So you can see we're on a GPU session here. I can't actually remember how you change this the type of session, but you can change the type of session to a GPU one if you don't have it, and that will load the model into a GPU, and it'll just be a lot faster. So let's actually, I'm just going to go ahead and try and run this in real time. I think we've got time. Yes, run anyway. Hello. Okay, so once we've loaded the model and all of the weights for that particular model, then let's start having a bit of a play with the sentiment analyzer. So this is another model that I'm using to detect the sentiment of a tweet, and I'm downloading that. Still installing stuff. Okay, now we're importing. Now we're downloading the model. 500 megs for this model. That is a lot of parameters. Now downloading the sentiment analyzer. And then finally, I'm calling the sentiment analysis model with some example tests just to see how it performs. Okay, cracking. There you go. So you can see the output of the sentiment analysis here. It's got 3 labels. They roughly translate to negative sentiment, neutral sentiment, and positive sentiment. And so if we select the second one, we can effectively positively reward the agent with when it produces positive text. Okay, so now we're going to take some seed phrases. Now this is actually a bit tricky. It took me a while to find a couple of phrases that were sort of interesting seeds to use for the generative parts of the as the seed for the generation. And you kind of need to think about, you need to think in the mind of Donald Trump. How would you start a sentence if you were Donald Trump? And so, but you also need to leave it quite open so that it allows the LLM to kind of generate, possibly negative or possibly positive sentiment. They're kind of good test phrases there. So let's add another one in here. My thoughts are, and I know the weather today is okay. So that's what I'm going to do. Right, now we're going to set up the environment. So if you remember back, one of the most critical parts of any RL problem is the environment. The author of the library has already created a text-based RL environment that contains most of the functionality. So take a look at that if you're interested in that. But I'm going to overwrite and override the reward function here because I need to specify my own reward function. And basically, we are taking the predicted text. So think of that as that's the new observation, basically. We're tokenizing it. And then, sorry, we're not tokenizing it. We're converting the tokens back to a full string again. And then we're running a sentiment analysis on that. There's a bit here where I'm multiplying it by 10 just to basically bump up the reward a bit more. It turned out if you just left it as between 0 and 1, it just didn't change the model quickly enough. So I just added more reward until it started to do that. And then we're finally developing or defining the RL algorithm. Here we're using one out of that PFRL library. It's just a PPO implementation, which is an on policy, it's a robust on policy RL algorithm, which means that it doesn't work offline. It works purely online. So it needs a simulation to work in, but it's robust in the sense that it doesn't jump too quickly, too often. And there's a bit of statistics and maths behind that, but basically when it's updating its model, it takes reasonable updates. It doesn't jump off in one direction, get it completely wrong, and then jump off in another one and get it wrong again. And it works very well in practice. So we're going to create that now, and this is the initial prediction using the raw untrained model. So you can see here that we've got our prompt, I really, and then don't know what to do about this, don't know what to do with it, I don't know what to do with it, I don't know what to do with it, I don't know what to do with it. Okay, the LLM is obviously having a little bit of a breakdown there, doesn't know what to do with it. And my thoughts are with the people of the United States of America. There we go. This is more Trumpian. This is great. We will always stand with them. We'll always defend our borders, defend our values of family and community. Community is really important. And the weather today is very bad. We're going to have a big landslide. Get out and vote. Okay. I think we've got slightly mixed messages going on there, but that's really great. Okay, so that's what happens with the model before we start fine-tuning it. Now we've got this massive helper function, which is basically doing the RL training loop. It's running for a certain number of steps, certain number of iterations, and it's going to continuously generate some new text using the LLM. It's going to feed it into the agent. The sentiment analysis is then going to give it a reward. The reward then adapts the model, and then and this is the crucial bit. Actually, I forgot to mention it. So the action of the RL agent is being used as the input to the LLM model, like the raw embedding, the raw vector embedding. So if it's, I mean, I don't know in this particular model, I don't know how big it is, but typically it's something like 500 individual numbers that represent the embedding of the text in 500 dimensional space. So you imagine a point in space. So this is the embedding for that sentence. So that's kind of what it's that's what it's altering at the input, and so that allows it to change the output and change the position of the embedding in that space. And it'll keep doing that and going round and round and round in circles until it's kind of shifting it to a more positive area in that space. So that may take some time. So hopefully, yeah, okay. So if you leave that for a while, it will eventually train, it'll save it in some output folder, and then we can reload that best model. It records the moment where the reward was highest and retains that model. And then we can reuse that model again to do a predict function. And I really wanted to see what the output of this new one I've just added, the weather is today. But you can see that the new outputs here now I really love this. So that's had a huge effect, completely changed that sentence. My thoughts are, with the people of Flint, Michigan, we're working hard to restore your water and restore our power to our great people. We are working hard to protect your Second Amendment. Okay, so it's still relatively Trumpian, but well, let's compare that to the first one. It's a little less aggressive, a little, but not much. So anyway, so we have changed that we have changed the underlying sentiment of the LLM effectively with this experiment. In real life, I think we've just cracking, we've just done. Right, I'm gonna reload that best model. That's not very positive. The weather today is a mess. Well, actually, right now in Europe, it certainly is a mess. It's 40 degrees C is not good, but not particularly positive in this case. Anyway, fun stuff. Obviously in real life, the reinforcement learning framework is actually used to nudge and fine tune the underlying weight in the model. And they do that by they do that by asking people whether the generated content was either good or bad. They gather that feedback, and then that becomes part of the reward. And then depending on that reward, then that information is fed back to the weights in order to nudge the underlying model in a specific direction. So yeah, it's a little bit more complicated than that, but that's kind of the premise of it, and it works really well. So that's used very often with LLMs, generative LLMs especially. But of course, you can use that in any ML model. You could use reinforcement learning based fine tuning to tweak the models of any model. So interesting use cases there. Okay, no questions yet, so I'll just crack on. Feel free to ask any questions if you've got them. The next example I'd like to go through is this introduction to RL. So if you go back to the repo again, this is the slightly older example, but this is a little bit more in depth, but it really goes into the details. You saw in that first example there that the majority of the functionality is all abstracted away with these giant helper functions, especially this giant train function here. This RLENV, you can't really see behind the scenes there. So let's actually have a look at an example where we're writing everything from scratch, including the RL algorithm. So if you weren't here in the sort of previous two presentations, then let's just quickly recap what we're trying to do here. So reinforcement learning is a way of attempting to solve or optimize a Markov decision process, and that's often known as an MDP. And it's a framework that allows us to model specific sequential decision-making problems. Basically, there's two key entities. There's an agent, and that is going to be our model, our algorithm in this case. What we're trying to do there, the agent is trying to learn strategies or learn techniques to perform better. And there's an environment, and that's everything else external to the agent. And in this case, again, we're going to use a simulation. We're going to write the simulation, but in real life, that could be real life. The things that come out of the agent and into the environment are the state or the observation of the state that comes from the environment and is fed back into the agent. That's there to provide the agent with information about what the current underlying state of the environment is. The action, the agent then produces an action, and this is what the agent would like to do within that environment. That typically affects the environment in some way, so the observations will be affected. And finally, you receive a reward, and the reward is the thing that is the environment telling the agent that this was a good action or this was a bad action, and it uses that signal to do more good actions in the future and less bad ones. And imagine it as a loop. It's going round and round and round and round. Equally, imagine it as a tree. You're rolling out all of these action decision points. So it's action one way, action the other, so on and so forth. All right. One of the classic RL simulation environments are based upon a grid world. A grid world is like a chessboard or a checkerboard or a drafts board, depending on where you're from in the world. And it's got squares, and your agent can move from one square to another in a range of different ways. They're quite interesting because they're simple to visualize, they're simple to understand, but you can actually map it to a fairly large number of problems and assign relatively realistic events inside each one of those states. You can, so in our example, we're going to use a classic form of the grid world here, where we've got holes in our environment and the agent can fall down the hole, and we don't want to do that. So let's start going through the code. First, I'm going to define how the agent can move. We've got points on the board and we've got directions up, down, left, right. I've used Unicode here to make it a little bit more visually appealing. We'll see that in a minute. And then we can start defining our environment. So defining a class for that. Oh, of course, I didn't mention actually. So all of this and all of the other examples and a lot of RL work in general is done in Python. I am actually yet to use any other language to work on an RL problem. Interesting challenge there. So now we're defining the environment. The environment has some internal state representation here that we usually wouldn't be able to see, but in the simulation, it needs that state. It's got a width, it's got a height, it's got an action space, so forth, so on and so forth. Then the next thing we need is a reset function. So this is interesting, actually. So typically when RL agents are trained, it's usually a very good idea to try and train them in such a way so that you can easily iterate over the environment. If you can reset that environment back to some starting state, it doesn't have to be the same state, could be a random state, but if you can reset it, it really helps the agent reground itself. So imagine you've got a problem where you're doing some robotics thing and the robot has fallen over or something. Like, you could teach and allow the robot to learn how to get back up again. It's much easier just to reset the environment and start again. So it depends on what you're doing, but in this particular case, we are going to do a reset. It also makes it simpler from a performance measurement point of view. You can just look over one full episode. They call it an episode, where you go from a starting state, lots and lots of actions, and then a terminal state. One full episode is a nice way of defining performance, like how well did you do within that one episode, but not applicable to all circumstances, obviously. Okay, so we've got a reset function here that is setting the agent back to a specific position. Basically 0, 0. So it's the same position each time. And then we've got a method here to take a step. So depending on what the agent selects, it can select a direction to step in. Then we're going to update the underlying state of the environment. So it's just a big nasty set of if statements to figure out where we are after we've moved. If the agent tries to move off the board, they do not move at all, are put back in the previous position. And if they've reached the goal in this environment, then we terminate the episode, and that's it. Also, here's the reward function. So this is an interesting one. This is a really simple reward, but it works really well for these types of problems. If you provide a constant negative reward, then effectively what you're doing is you're trying to emphasize that it takes energy, it takes effort to move. And so we're going to try and get to the reward, the goal, sorry, in as few steps as possible, which is quite commonly the requirement for an agent in this kind of situation. But really simple reward in this case. This is our reward function. And then we are passing back all of that information, the new observation, the reward, and whether it's terminal, back to whoever called this method. Bit of a helper function here to represent the agent in a visualized way. And then now we can give it a go. So I'm instantiating the class and then running the agent through a series of steps. So the agent is denoted as an X in this image. We are giving it a direction to move in, and it prints out the new state of the environment, where the agent is in that environment at each time step. The circle here is the target, the terminal point in this grid world, and then when the agent has reached it, it'll turn to a little @ symbol. Okay, hopefully that all makes sense. Yep, so a couple of key things to take away from this. Yeah, the state is the observation of the environment. In this case, we have a very omnipotent view of the state. We can see where the agent is within the state, within the environment. Quite often in these tasks, the more difficult versions of these tasks are where you just have a camera, a view, a local view of where the agent is. You don't know, the entire state of the entire environment. The reward is the only thing that is encapsulating the way to solve the environment, and it's a very simple one in this case. And it's still used fairly often, actually, in many RL algorithms. And finally, the action. Yeah, every action mutates the environment in some way. Ideally, you want it to be observable to the agent again, so that it can learn that its actions has consequences. Okay, so how do we actually solve this then? How do we find a path through this environment? And of course, we could edit this environment. You could make it bigger. You could make it smaller. You could start adding things in it. You could add rules to that big if statement there to, add some new blocks in there so it can't move through certain states and things. You can make it a maze. So how do we go about solving this? Well, one of the classic ways of solving it is using an algorithm, an RL algorithm called a Monte Carlo algorithm. So remember that this isn't a one single decision. We can't just look at a state and then pick which direction to go, because it might depend where you are. So if you're at the top left corner, for example, up here, it probably makes sense. Well, I can't. Do I have diagonals in my directions? I don't think I do. I think I've only got ups and downs. Yeah, ups and downs and lefts and rights. So if we're in this top corner, it makes sense to either go straight down or straight across and then straight down. That's probably the most logical. I don't know, but you could argue you could go down then left and down then left and down then left. But anyway, how do we actually learn what is optimal here, and what is optimal in this specific state? Is it better to go up? Is it better to go across? So what we're trying to do here is to form a general way of solving environments like this, to provide us with an optimal path to the end goal. Monte Carlo based solutions. Monte Carlo comes from the place, Monaco. It comes from the idea of randomly sampling, of randomly trying lots of things, and attempting to effectively just record what the outcome was. And if the outcome was good, then we should encourage that. If the outcome was bad, then we shouldn't encourage that. So the general implementation of a Monte Carlo algorithm is basically randomly move in one direction, check to see if you've reached the goal. If you haven't, then just keep doing that. If you have reached the goal, then what was the total reward over that entire trajectory? Was it good or was it bad? If it was good, then let's try and remember those steps so we can do them again. Okay. So this is all from chapter 2 of the book, if you want to learn more about it. So what we need to do is we need to develop some methods to do several things. The first thing we need to do is to generate a trajectory. So how do we do that? Well, basically this is we saw that helper function before that encapsulated that massive training loop. Inside that, there is there will be a bit of code that runs it for one trajectory, for one single episode. And that's what this code is doing here. We're starting with a buffer, and then we are running around in a while loop whilst it's not terminal, and we are collecting states and the results of those states in the buffer there. Our actions are randomly chosen, so entirely random. There's no intelligence there. And we see what happens. We keep doing that until we get to a terminal state, or we reach this max steps parameter, which prevents it from just going round and round and round and round in circles. Okay, so that's the generation. Now let's just visualize that again. This is one of the trajectories generated here. So the agent is probably not really doing anything. Oh no, we've got a bug in our code. Where's the agent gone? It looks like it's somehow gone from the left-hand side over to the right-hand side, like Pac-Man. It's been teleported, but that shouldn't be possible. Okay, so extra bonus points if you can figure out the bug in that giant if statement there and send me a fix. Sorry about that. Where were we? Yeah, so that's just basically randomly moving around. And on this particular trajectory, oh, it didn't quite make it. Look at that. We're one step away, but it still didn't quite make it in time, and it was terminated early due to too many steps. Okay, the total reward for that entire episode was -10, because remember, we get -1 for each step. Okay, so how do we start trying to figure out what a good trajectory is? One way of doing that, and there's a couple of different ways in RL, but one way, and probably the simplest and easiest to understand, is where you record, on average, the value of being in a particular state. So, for example, if you imagine that you are right next to the terminal state, the goal, then if you go, if you're directly above it, if you go down, then there's going to be a penalty of -1. There's going to be a reward of -1 to get there. But if you go up, it's going to be at least a reward of -2, because you've got to go up again, up, and then down again, and then down again for a second time. So at least -2. So the value of choosing the up action in that state should be -2 if you're picking the right combination of options. But the value of picking the down action in that state is -1. And that's kind of true for all of the directions. We can look at all of the actions and we can see that actually that -1 is the highest reward that we can possibly get, and therefore it's best. So effectively what we need to do is we need to sample all of these trajectories and record how far away they are from the terminal state. And if you were to generate that matrix that records that average value of being in a particular state, or the average value of picking a particular action in a particular state, That's called a value function, or action value function if you're using actions as well. And what that is in this scenario is a big lookup table where we just have a key, which is the position and action, and the value is the current average value of taking that action once we've got to the terminal state. Okay, so that's what this is. That's what's being implemented here. A couple of helper functions. We've got an action value calculator here, where we are taking the summed up values and the number of times that we've visited that particular state in action pair. So it gives us the average action value, returns 0 otherwise. Then we're going to run that episode. So we're going to generate loads and loads and loads of trajectories, and we're going to add all of the values to that buffer. And here is one of those examples. So you can see that the values that have 0 have not been visited at all. We're also, what are we looking at here? Oh, we're looking at a particular direction. We're looking at a particular point on the board. So this is 0.30. So that is the state that is, I think it's this one here. It's just to the right of the terminal state. And so you can see that, oh, and let me just remind myself which up is 1, is index 0. Right is index 1, down is index 2. So I think what we'd expect is that this second state here, yeah, so that's right. That's right. So the second state should be equal to a value of 1 on average, because whenever you are in that state next to the end and you pick the direction of right, then the average amount of energy spent to get to the terminal state is -1. And you can see that that's correct. So this is the first time around this iteration loop. This is the second, this is the third. And you can see that on the first time that most of the values are 0 because that action was never sampled. This one on the edge was. So this corresponds to so it's north, east, south, west. So this is actually moving away from the terminal state. And you can see that it took 8 steps to get back to the terminal location again. So we can run around that loop again and again and again, and we get a better sample of what happens when we actually perform many of these actions from this particular state. And you can still see that the right action is still the highest, it's still the best. And the second best would be to, yeah, apparently the second best is to go left, because then you can come right again. So yeah, now if we run that a bit more, we can start to see some patterns emerging. This is a plot of the average value of a particular state. So this is the action value for a single state. So you see how we've got 4 numbers there for each of the actions. If we then average those together, we get a single figure for a single state. And that's what this is here. So you can see in general, there's obviously noise in a lot of in this because we haven't run it for long enough yet. But you can see that in general, it's better to be close to the terminal state than it is to be far away. Okay, so this is after now 1,000 iterations, and so we've got a much better sample of data now, and the averages are coming out much more reasonably. And then finally, we can look at the individual actions in each of those states and pick which is the best one. And you can see that when we're getting close to the terminal state, it's generally pointing towards the terminal state. There will be some fluctuation because obviously in this state, it doesn't really matter if you go right then down or down then right. They both lead to the same location in the same number of steps. So you will get a little bit of noise in some of these directions. you can also see there's a bit of an issue at the top here. It's saying that at the starting point, the best action is up. Now, I think that this is probably that bug that we saw earlier. So that's interesting. So that just tells you, that just highlights how how hard it can be sometimes. This is in a ridiculously simple environment, and there's a bugging there which is affecting the optimal policy. I haven't actually mentioned that yet. So imagine what it's like when you've got a much more complicated environment. You need to be so careful not to introduce bugs because, yeah, it's so easy to get it wrong. And that's why visualization is so important. It's just visualize everything as soon as you can in the best way you can, and it helps you spot some of these issues. All right, so an optimal policy now, we can actually derive an optimal policy by simply following this action value function. Just on each time step, pick the best action, pick the best action, pick the best action. And that will eventually lead you to the result. Yeah, and that's it. Oh yeah, you can see that bug in the final one final run. Yeah, so this is sort of a final clean run again, just to generate a new policy, and you can see that there's a bug. It's actually found our bug. It says that we can move left and teleport to the other side of the board and just go straight down. Yeah, and it's taking advantage of that. That is hilarious. But yeah, and there you go. So that is one way of solving an MDP. It's a Monte Carlo based algorithm. It's a really good baseline. It's great at generating trajectories for visualization purposes. The downside of it is that it's not very efficient. So the more efficient algorithms, so the next step in the evolutionary tree of RL is that they start to incorporate knowledge about what they've observed as soon as they have seen it. So they incorporate it during the episode. They don't wait until the end, like we have done here, to generate an optimal trajectory. So yeah, but so basically we've sampled all possible states here to generate that trajectory. In the real world, that is infeasible and intractable. You can't possibly sample all possible states because there's usually an infinite number of them. So yeah, more modern or more evolved RL algorithms attempt to use that knowledge earlier on and actually start to use that optimal trajectory during the generation process as well. So it doesn't waste time going to locations which are not going to be fruitful. Okay, so that's it. So there's lots of ways that you could alter this. You could fix the bug. That would be a great first step. You could start adding some traps or some mazes or other things there. You can make it bigger. What happens when you make it bigger? Does it get to a certain size and it becomes infeasible to run? What else could you do? You can start playing with a reward function. Can you use a more realistic reward function, a better reward function? What happens when you don't give the agent a full view of the full state? Does that affect things? Yeah, lots of things that you can do just to have a play and get used to working with these things. The next step to move past this would be to start considering more advanced RL algorithms, start exploring different exploration methods, pun intended. What else could you do? Yeah, and I think the next big step would be to consider a more realistic environment. But don't try and take too much of a jump because, as you can see, the environment is key. If you get the simulation wrong, you introduce bugs. You may, so for example, if you add a bug into your simulation and you try your RL algorithm on it and it doesn't work, you get disheartened and you tell your boss that RL doesn't work for our problem. Could just be a bug. And it was so hard to know. So yeah, start developing an environment for your specific domain. Take it step by step. Do it really simply. always use very simple randomized based algorithms as a baseline. You'll get to a point where it's actually not, it's impossible for it to solve the environment. But there are still sort of equally similar simple algorithms that should be used first before you jump into a deep problem, a deep reinforcement learning algorithm or something like that, just to make sure that the environment is working and it can be solved effectively. Okay, so I think just for the final few seconds, I'll leave the slides up so you've got the links there. And oh, that's just completely destroyed that. I'll just leave it like that. And I'll just wait to see if there's any questions. But apart from that, I hope you've enjoyed that series. It's been very long, very detailed. I appreciate that. So thank you so much for sticking with me. If you've got any questions at all about it, then feel free to reach out, Phil@Winder.AI. If you've got any business related, if you've got any RL related business challenges that you're facing, if you're thinking about using RL in your business, we would definitely love to speak to you. That's what we do full time at Winder.AI. So yeah, definitely love to talk to you. And of course, if you hear of anyone wanting to do that, we'd really appreciate the referral to those people as well. And if you're interested, buy the book. And I'll leave it there. Thanks so much. Thank you. Okay. Welcome back again. I've just spotted that we've had a question from Ramon. Thank you so much, Ramon. Actually, I'm just going to hide this now, and I'm going to see if I can show that question. Yay, it works. Can RL be used to find bugs in environments, such as games, for example? Absolutely, absolutely. Yes, they can. If you have a reward that is attempting to solve the game, win the game, you could just allow the agent to explore and test that environment until it breaks. So this is actually true of not just games, but things in real life as well. So one of the examples I gave in the first part of this of these presentations was an example that we did for penetration testing for specifically SQL injection and attempting to defeat web application firewalls by using reinforcement learning to generate commands that exfiltrates data. So we're finding bugs in the firewall to obtain sensitive data. And so the goal in that case is finding sensitive data, getting through that firewall. And you can consider it a game, you know, it's like a classic sort of adversarial type game. So yes, definitely applicable to all kinds of problems relating to adversarial play. Okay, any more questions? Thank you so much, Ramon. Appreciate it. No more questions for now. Yeah, another thought I've just had actually is obviously like, yeah, games are a big are important in RL. Like a lot of the early examples and breakthroughs demonstrating RL were in games, like traditional board games originally. But there's absolutely no reason why that can't be extended to more modern games. I remember speaking to one chap that worked for a mobile gaming company, and they had an interesting problem that they were considering using RL for. They said that their customers, their users, they actually didn't like it when the game got too hard. And so they were using like a traditionally generated sort of AI bot to play against that player. But they found that the bot was kind of too clinical. They were too clinical. They were too good at what they were doing. and the players didn't like it. They had a drop off in the number of the retention of the players because the bot was too difficult. So they were looking at using reinforcement learning to actually to become the AI, the bot that was playing against them in this game, but actually behave more like a human, like make mistakes and do silly things when you're not expected and things. So it's actually an interesting example of the opposite there. Kind of, you're not trying to break the game, you're not trying to win the game, you're actually trying to optimize for user enjoyment, which is definitely possible in reinforcement learning because the reward function is so flexible. But you're almost detuning the AI there. You're trying intentionally playing worse than it can. So yeah, interesting idea there. Okay, cool. I think that's about it. No more questions. Any more, feel free to reach out over email. Thanks a lot. Have a good night. Bye-bye.